quick 6-minute deep dive for YouTube. For centuries, we have stood on Earth and wondered what forces can gouge a planet. Then looked outward and found Valles Marineris, a canyon so vast it would swallow the Grand Canyon many times over. What carved the solar system's most dramatic canyon? I'll tease a mystery. 10 clues, descending from plausible to most likely. And by the end, I'll give you the best current answer science offers. In this countdown, we'll touch tectonics, volcanoes, ice water impacts, wind, the slow handiwork of collapse and debris. Each clue is a chapter in a planetary detective story where evidence is in rock layers, fracture patterns, and landscape scale. Stay with me. The most persuasive explanation synthesizes many actors, but one plays the starring role. I'll guide you like a curious narrator, pointing to data, reasoning through history, and revealing the conclusion at number 1. What carved the solar system's most dramatic canyon? Number 10. Massive crustal stretching during Tharsis uplift toward the ground, forming long rifts, a prime architect of Valles Marineris. Imagine a planet's crust under enormous tensional stress as a colossal volcanic province swells nearby. The surface responds by cracking, and those cracks align into long troughs that trace the stress field. The linearity of many Valles Marineris troughs and the scale of many troughs match what we expect from tectonic rifts driven by Tharsis's inflation. On Mars, without plate tectonics like Earth's, localized stretching from huge volcanic load can still deform the crust dramatically. The orientation of faults radiating from Tharsis and the depth-to-width ratios of the troughs make tectonic rifting a foundational clue. Tectonics sets the stage, creating the primary geometry that subsequent processes would exploit and modify. Number 9. Underground magma uplifted and fractured the crust, prying the surface apart and enlarging fissures. Magma doesn't always erupt. It can intrude and blister, pushing upward like a thumb under a tablecloth, producing radial fractures, producing concentric fractures. In the Valles Marineris region, dikes, intrusive bodies, volcanic constructs suggest magmatism amplified the rifting. Magma-driven uplift can locally weaken rock, concentrate strain along existing faults, allowing small cracks to grow into canyon-scale gaps. Thermal effects from intrusions thermally alter the crust, mechanically soften the crust, making it more susceptible to collapse and erosion. So volcanism is not merely decorative, it's an active collaborator in canyon formation. Number 8. Emptied chambers and weakened layers collapsed, creating sink-like stretches that joined into a canyon. When subsurface materials are removed, magma withdrawal, volatile loss, dissolution. The overlying rock can fail catastrophically and collapse into voids. Repeated collapses along linear weaknesses coalesce into elongated depressions large enough to be recognized as trough segments. Collapse structures leave telltale signatures: chaotic, blocky terrain, isolated mesas, steep-walled pits that link up along faults. On Mars, where subsurface layering and volatile-rich deposits were common, collapse is a powerful mechanism enlarging and deepening pre-existing rifts into a contiguous canyon system. Number 7. Circulating groundwater could have dissolved and undermined rock, carving channels from below. On Earth, subterranean water can erode transport and weaken strata until overlying rock collapses, producing collapsed sinks and extended valleys. Mars's early warmer epoch plausibly hosted groundwater systems. Fractures from rifting would focus flow and allow subsurface erosion to act along the canyon's spine. Mineral evidence, altered rocks, and paleochannel remnants hint that fluids once moved through Mars' crust, chemically altering and mechanically removing material. Groundwater doesn't need to carve the entire canyon, but it plausibly hollowed and softened structural highs and lows, facilitating later collapse and widening by other agents. Number 6. Ice-rich flows, glacier movement scraped and gouged valleys that later widened. Cold-based glacial activity leaves striations, moraines, polished surfaces. On Mars, near mid-latitudes and highland troughs, implies ice may have occupied parts of Valles Marineris. Ice can be both erosive and supportive, carving by flow, later melting, or sublimation that undermines valley walls. Glacial deposits act as lubricants for mass movement, producing debris flows, modifying trough floors and margins. While glaciers might not have sourced the original rift, they could have reshaped trough interiors and contributed to the canyon's present morphology. Number 5. Steep, unstable walls collapsed repeatedly, adding debris and deepening the trough. Valles Marineris displays spectacular landslide scars, hummocky deposits. When a wall fails, tens of kilometers of rock can travel and excavate. Recurrent mass-wasting smooth slopes, buries terraces, continually remodels canyon cross-sections. Such failures are a natural response to oversteepened cliffs created by rifting and collapse. Ice melting, seismic shaking from tectonics or impacts, long-term erosion all trigger slides. Over geological time, the accumulation and removal of landslide debris materially widen and deepen the canyon's profile. Number 4, giant impacts sent shockwaves and fractures across the crust, seeding large-scale cracks. An energetic impact fractures rock on a planetary scale, creating radial faulting patterns, creating concentric faulting patterns that can be exploited later by tectonic stresses. Impact-triggered weakness could have focused where rifts initiated, where fractures propagated preferentially. Even if not the primary cause, impacts provide triggers and pre-weakened zones that interact with tectonic stress fields that interact with volcanic stress fields. Mapping of fracture orientations sometimes correlates with distant impact basins, suggesting impacts contributed to the canyon's fracture architecture. Warm rim light. Number 3. Explosive release of subsurface gases could blow apart rock and propagate fractures. Mars harbors volatiles, carbon dioxide, water vapor, other gases locked in subsurface deposits. Sudden release under low atmospheric pressure can be violently erosive. Patches of chaotic terrain and vent-like features point to past pneumatic events that stripped fines and enlarged fissures. Gas-driven explosions fragment rock into mobile grains transported by winds, mobile grains moved by gravity flows. While gas eruptions alone are unlikely to carve the entire canyon, they can significantly weaken and disaggregate crustal blocks, accelerating broader erosional and collapse processes. Number 2. Persistent Martian winds slowly widened pre-existing faults, removed loose material over eons. Mars' thin atmosphere nevertheless moves enormous quantities of sand and dust, capable of abrading cliffs, filling trough floors, scouring trough floors. Aeolian processes polish cliff faces, scour channels, redistribute debris from landslides, incrementally widening the canyon. Wind is a slow artist but relentless. It especially excels at removing fine-grained, weakly cohesive materials left behind by collapsed volcanic ash. In the canyon's later history, wind has been a primary modifier, repainting details, exposing the scars of older processes. Number 1, most likely, tectonic rifting tied to tharsis created the primary troughs: volcanism, collapse, water, ice activity, landslides, wind, all modified and widened the canyon into the Valles Marineris we see today. The simplest, most explanatory narrative begins with a colossal tectonic response to Tharsis's rise. Crustal stretching forged the linear architecture. From there, magma intrusion collapse of voids, circulating groundwater episodic glaciation mass, wasting impacts Aeolian reworking, each left distinct fingerprints. Science rarely hands us a single culprit for such a complex landform. Instead, we read a composite ledger written in rock and dust, where the dominant entry is tectonic rifting initiated by volcanic loading, and every other process supplied crucial edits. That multi-agent narrative best fits the morphology, structural patterns, and geologic context recorded across the canyon. After our countdown, the evidence points to a layered story. A tectonic curtain drawn by the Tharsis Rise opened the stage. Volcanism, collapse, fluids, ice, impacts, landslides, wind, all performed acts that shaped the canyon's final form. This is the beauty of planetary science. Not a single dramatic scene, but an epic with many acts, each leaving clues we can still read. So the canyon story is a mystery solved by many forces, but tectonics take the starring role. If you want deeper dives into any single theory, tell me which one in the comments. I'll be back with more explorations, unpacking the mineral clues, the orbital data sets, and what future missions might reveal. For now, carry this image. A planet reshaped by internal power and patient surface agents, recorded in a scar visible across millions of years. So the canyon story is a mystery solved by many forces, but tectonics take the starring role.